afternoon. I'm delighted to be back here again. So it's my pleasure to, again, share our perspective of what's the energy outlook going forward. And the way we utilize energy is not sustainable, right? Today we emit essentially 40 gigatons of CO2, and is ever increasing, right? So going forward to 2050, essentially we're looking at 10 billion people, 2 billion cars. We need essentially advanced technologies to essentially transform how we utilize and how we distribute energy so that we could essentially have more sustainable future. So we believe electrochemistry plays a very important role in enabling this sustainable energy future. So today, if you look at electricity, wholesale electricity is essentially free, right? So electricity comes from solar farm, you're looking at 1 or 2 cents per kilowatt hour, right? Now, if you look at electricity stored, right? So for example, electricity for lithium-ion batteries used in EVs, we're looking at $150 per kilowatt hour, right? So stored electricity is much more expensive than the wholesale electricity. So the storing electricity or storage technology is very important to enable essentially the wholesale electricity come from renewable sources to be used in our transportation and to be used in our buildings to reduce the CO2 we emit today. Electrochemistry, right? So essentially we convert electron energy to make chemical bonds, right? Or essentially have the reverse process, right? So one is energy conversion, the other is, one is energy generation, the other is storage. It's very analogous to pumped hydro. Right, so in an electrochemical reaction, essentially you let the electrons going downhill, right? And the energy generated is really the gradient or the energy difference of electron will flow downhill. And we store essentially electron energy in chemical bonds. And using this technology, we can actually have much higher stored energy density relative to pumped hydro. We could have, on the system level, energy density on the order of 1,000 watt-hour per kilogram. So over the past a few hundred years, right, scientists, engineers have been working on essentially mastering or changing chemistry in order to increase the stored energy, right? Since the invention of batteries by Volta in 1799, right? So initially, the first 100 years, we're looking at utilizing redox of transition metals in aqueous electrolyte, right? Such as the batteries we use in cars, lead-acid batteries, nickel metal hydride used in hybrid vehicles, right? So essentially, redox of transition metals, typically 1 or 2 electrons in aqueous electrolyte. And then these systems are limited by really stability of water, right? Stability window of water, right? Up to 1.2 or 1.5 volts, typically in practical devices. Right? And lithium-ion batteries utilize essentially non-aqueous electrolyte. We're no longer limited by stability window of water, right? So we can have a system per cell that up to 4.5 volt and significantly increase the energy and power of our storage devices. And lithium-ion batteries, essentially the technology dominant the market for transportation, right? So EV hybrid vehicles. And it's also becoming the major technology for essentially grid applications. But we would argue that going forward, right, if we want to utilize storage technologies, storing electricity to essentially displace the amount of energy we use in the world, essentially utilizing lithium-ion battery technology where essentially we store each electron utilizing a transition metal, each transition metal, such as cobalt or nickel. And there is actually not enough cobalt or nickel to power all the vehicles, right? We have today, where all the vehicles will have 2050. So developing technologies that focusing on earth-abundant elements, particular elements in the right-hand side and the right-hand side of periodic table is very important. For example, sulfur, oxygen chemistry becomes very important if we want to essentially displace replace the technology or the energy we use and storing the energy in chemical bonds. So the reason lithium-ion battery technology dominate transportation is because over the past decade, the cost has dropped 10 times. So it becomes a technology of choice for electric or different degree of hybridization in vehicles. And in addition, starting 2016, it also becomes the major technology for installed power for grid applications, amounts to essentially 90% of the total installed power for grid applications. So that's the technology that you're going to see in the next 5 years, 10 years, perhaps 15 years, and that's the technology you can do techno-economic analysis where you can see which state, which region, which city, how you're going to utilize this technology that can generate value immediately. But the technology we have today is not perfect, right? One would argue is far from perfect. There is an issue of thermal instability, particularly upon charging of the batteries. The positive electrode can generate oxygen. It can react with electrolyte. The electrolyte is organic electrolyte, and essentially can generate heat and leads to a thermal runaway. So there's a need to move away from organic electrolyte and replace it with essentially safer solid-state electrolyte, either polymer form or inorganic electrolytes. And with the development and the use of solid-state electrolyte, not only we can improve the safety of lithium-ion batteries, we can also potentially enable the use of metallic lithium instead of the graphite we use today, right? So if we can enable use of metallic lithium, right, they can potentially double essentially the energy density of lithium-ion batteries. Right. So the question is, how do we find really the solid-state electrolyte that can conduct a lithium ion as well as a liquid? And as you can see from this chart, right, so the vertical axis is ion conductivity, lithium ion conductivity, and the horizontal axes are really just different structural families. As you can see that there are many structural families where you can conduct lithium ion as well as a liquid in a solid state, right? So the challenge today is essentially none of these electrolytes are stable against the positive electrodes we use today, nor the negative electrode we use today in lithium-ion batteries, right? So the question is, we essentially need to search for more electrolytes, right, that can be not only conductive, but also equally stable against the positive and negative electrode to be enable essentially stable solid-state lithium-ion batteries. Right? And as you can see that within each family, the ion conductivity can vary by many order of magnitude. Some are over 10 order of magnitude. Right? This is really through the development over decades through cation substitution or anion substitution, 3 decades of work that researchers has found the right recipe where you can have liquid-like conductivity, right? So now we say, okay, now they're not stable, then how do we begin to discover new electrolytes, right? So can there be faster methods? Can we find the design principles where we can look at a library of large number of materials or chemistry? What is really the parameter or a physical origin that influence the conductivity of, for example, let's say the lysicon structure? That you can see that with conductivity varying 10 order magnitude. And what we find recently is that if you look at the phonon or the phonon energy, phonon density of states, right? So essentially is how fast essentially the lattice would vibrate, essentially is coupled with the energy barrier that lithium will move through the lattice, right? What we find on the right-hand side is the migration barrier essentially correlate with the lithium phonon band center, or the average vibrational frequency of lithium in that particular lattice, right? So across essentially large number of compounds, not only in the lysicon structure, but also in the olivine structure, right? So this is essentially what we find is one of these first universal design principles. You can play with phonon density states that you can influence and dictate lithium mobility, right? So if you want to have a stable structure, right, only conduct lithium, but without the other ions moving, essentially we would like to have the other inactive or non-mobile cations to have very high phonon band center, right? So this is essentially the key design principles. You want to have softer phonons for the mobile species, but essentially harder phonons for the structural ions. So we're currently essentially utilizing this design principle to see can we generate a large amount of database for the phonons through which we can actually do discovery and design of new electrolytes. Solid state electrolytes are difficult to process, to essentially make solid state batteries at essentially the same speed or at a scale. And quantum escape that Fritz started is really working on these very challenging problems, right? We know, and this may take some time for us to really innovate, develop essentially the technology that can make batteries at the current speed, right? But we know polymer electrolytes. We know we can process polymers at a very small thickness and also at scale and at speed, right? Unfortunately, polymer electrolytes, they're very poor conductors of lithium ion, right? So you can see from this graph, so on top, essentially, the either solid-state ceramic electrolytes or liquid electrolytes. And then essentially the blue dots are polymer electrolytes, or the best polymer electrolytes we got. You can see that at room temperature or near room temperature, we're at least 2 orders of magnitude lower, right? So this is one area that we're working on, right? So we have a relatively large team at M.I.T. with computational scientists and synthetic polymer chemists, and trying to design new polymer architectures, new polymer structure, where we can essentially develop design principles for polymer electrolyte ion conductivity, and potentially utilizing AI to infer essentially new polymer chemistries that potentially allow us to gain conductivity, break away the current limit that we have today. Now, as I mentioned earlier, we're still making better lithium-ion batteries, right? So using solid-state electrolyte, but the principle of storage is still we storing each electron using each transition metal. And if you look at the richness of cobalt or nickel, and if you do a simple calculation, how many vehicles we have today, if we're going to power all the vehicles with lithium-ion batteries, there's not enough cobalt or nickel, right? So then essentially, if we want to store energy or to power the planet, right, we want to utilize essentially Earth-abundant elements, right? The elements highlighted in the green region. So we want to utilize elements that essentially made out of, is actually in our rocks, right? So we'd like to promote the ideas is how can we develop technologies that storing electron using elements or using rocks. Right. So this is essentially another way to make the argument. Not only these elements are Earth abundant, if we develop systems, for example, metal oxygen or hydrogen oxygen, right, or lithium sulfur, they can provide much higher energy density, right, either on volume basis or gravimetric basis relative to the technology we use today, nickel metal hydride or lithium ion batteries, right? The challenge is that they're kinetically very slow and their efficiency are very poor. So this is really the scheme that we like to propose forward, perhaps for the long term, beyond 15 years, perhaps 20 years, where really 2050, if we want to power more large fraction of our vehicles or our buildings with electrons, and we need essentially high energy storage devices with elements that the Earth abandoned. Right? So we can utilize essentially the follow scheme. Right? So we take electricity from renewable sources, and we can do a water splitting, right, to reduce water to generate hydrogen as energy carrier, or CO2 reduction, nitrogen reduction to make ammonia. Right? So these are all hydrogen containing energy carriers. Or you can actually utilize the electrons, right, electricity, electrical energy, to reduce rocks, or metal oxides, right, and to generate energy carriers such as aluminum, such as zinc, right, such as magnesium, or one can even argue that silicon, right. So these can be all energy carriers, right. So this is essentially the energy storage step, right. You're storing electricity into chemical bonds. Right, once you have the electricity, or once you have electricity stored in chemical bonds, we can combine them with oxygen in fuel cells or batteries. You can combine with other, for example, Redox to make an energy generating device. Right, you can generate electricity and reproduce essentially chemicals, water, CO2, nitrogen, or metal oxides. These essentially compounds are stable under ambient conditions. Right? So you can see using these cycle, right, we have, during the storage step, we have oxygen evolution, regardless what energy carriers that we're generating. Right? And then once you have the energy carrier, you combine with oxygen, we need to essentially have oxygen reduction. Right? So oxygen, evolution of oxygen and reduction of oxygen are critical to essentially the efficiency of such energy schemes. Right? Not to say that CO2 reduction, nitrogen reduction are also very sluggish. Right? So using the best scenario, hydrogen, oxygen redox couple, we're looking at round trip efficiency on the order of, let's say, 50, 60%. Right? And this is much lower than what we have in lithium-ion batteries, which operate a round trip efficiency on the system level of 90%. Right? So we need to improve the efficiency or the kinetics of these reactions in order to make these technologies more competitive. So my son, who's 9 years old, turning 9, and he's been giving me advice about the talk. He said, I really need to make my talk more interesting. And so he gave me these jokes to say, that to make this presentation much more compelling. So he gave me these, so atom 1, so I heard oxygen went on a date with potassium yesterday. It went okay. Atom 2, I thought oxygen was dating magnesium. OMG. Atom 1, actually, oxygen asked nitrogen out first, but nitrogen was all like, no. So back to the kinetics. So we said that oxygen reduction, oxygen evolution are very difficult, and the consequences of that, essentially, if you operate a hydrogen-oxygen fuel cell, then you can actually have significant voltage loss for the device or energy loss of the device, right? So when you run at a finite current. So if you look at a voltage as function of current, essentially the shaded area on top that come from the losses associated with reduction of oxygen, evolution of oxygen, and hydrogen redox chemistry is very efficient. Now imagine if you're going to use nitrogen or CO2, essentially we'll have a comparably large energy losses, right? So the overall device will actually bear very little energy, right? So essentially we need to first, because oxygen redox is universal for all these production and use of these energy carriers, right? We need to figure out ways that essentially to improve the kinetics of these process, right? Regardless whether you operate oxygen redox in acid or alkaline solution, or at elevated temperature at the oxide-oxide interface, these kinetic limitation exist. One can design catalysts to essentially reduce the barriers between the reactant and product, right? So essentially, through the interaction of a catalyst, either you don't want a too strong interaction or too weak interaction between the reactant or product with a catalyst surface to enhance the rate. Right? So there are different ways to design catalysts or new catalysts to increase efficiency. Right? So there are many people at Stanford looking at a high surface area catalyst. Right? So the higher the surface area by developing a nanostructured materials, we can certainly enhance the geometric overall activity or the current. Or another approach is to look at fundamentally per site. Right? How can we increase the current or the activity for oxygen reduction turnover, oxygen evolution turnover per site, per true surface area? And that's an area that we work on. We're not alone in this endeavor, right? So over the past 100 years, there are many researchers looking at how to draw a relationship between activity descriptors or some parameter that may influence activity with the reaction kinetics. Right? So, for example, there's work of Jens Norskov correlating, let's say, the D-band center or electronic structure of metal surfaces to binding of different reaction intermediates, and through which they can develop reaction mechanisms, and through which they can screen different surfaces that can have high or low catalytic activity. And our contribution in the past decade has been looking at what type of oxide surfaces, right? What type of oxide electronic structure, right, may dictate the catalytic activity of oxygen reduction, oxygen evolution. Metal oxides are very important because if you operate in basic solution, you can use earth-abundant metal oxides to carry out oxygen reduction reactions. Right? And metal oxides are also very important for oxygen evolution, right? Because regardless, either in acid, in base, or in oxide-oxide interface, the catalyst catalyzing oxygen evolution is always metal oxides. Right? So if we want to promote oxygen evolution reactions, we need to figure out how water would interact with the metal oxide surface, what really unique electronic structure features of metal oxides would essentially dictate the turnover frequency of oxygen evolution. So I want to utilize a story of perovskites, in particular, how one can tune the metal-oxygen covalency as a way to control the oxygen evolution activity. So for metal oxides, electronic structure near the Fermi level typically will have metal D states, oxygen 2p states in a perovskite structure. So we have A site, B site is transition metal, and oxygen, O3. Right? So the electronic structure is very important. Essentially, let's say if you look at the Fermi level relative to the oxygen p-band center, it dictates the energy penalty to create oxygen vacancies. As you can see that as you push the Fermi level into the oxygen p-band, essentially there's very little penalty to create oxygen vacancies. Right? So the question is, if we push the Fermi level down, right? Essentially, that's we're increasing the covalency between metal and oxygen, and how would that influence the catalytic activity? As you can see from these two charts, two plots, right? So for both the oxygen surface exchange kinetics, which is the reaction exchange between O2 and O2 minus, right? And if you make the compound more covalent, right? So it's going from the left to the right, you can increase the exchange kinetics by 6 order magnitude. And similarly, that if you increase essentially the covalency for the oxygen evolution in basic solution, you can also increase catalytic activity by 2 order magnitude. Right? So this is essentially a correlation between measured catalytic activity, right, in different environments for oxygen evolution versus a computed oxygen p-band center. Right? So we all know that correlation is not a causation, right? So what's its physical origin that influence essentially this type of trend that increasing metal-oxygen covalency increase the catalytic activity, right? Unlike metal surfaces, and over the past few decades, there are large amount of measurements and computation knowing the electronic structure. And when we started this project 10 years ago, there's actually very little measurement of the density states for metal oxides. So we collaborated with Wang Li Yang at ALS and utilized X-ray emission spectroscopy and also X-ray absorption spectroscopy. We have to map out essentially the density of states for these perovskites, right? So on the bottom, a shaded area that occupied density of states measured by emission, and then the unfilled essentially is the unoccupied states measured through X-ray absorption spectroscopy. We can line essentially the density of states onto the same energy level and align them onto the absolute energy scale. Right? Once you align them on the absolute energy scale, then you can actually align the redox potentials of the solution species onto the same common energy scale. Right? So then you can actually, the dashed line, essentially the hydrogen redox and oxygen redox. Right? So from this picture, you can begin to develop energetic argument. Right? What is the barrier for my electron transfer? Right? What is the energetics for my hydroxylation of my surface? Right? So the degree of driving force hydroxylation is really the energy difference between Fermi level of your oxide surface relative to essentially the redox potential in the solution. Right? You can also look at what's the energy difference of my charge transfer by moving electrons between metal and oxygen. And so if you look at, let's say, a series of compounds, we done measurements over 30 some perovskites, right? So essentially from early perovskites to late perovskites, essentially you can increase the covalency of these metal-oxygen bond. And correspondingly, you can see that in gray bars, essentially the Fermi level come down. And also in the open bars, that unoccupied states, essentially for the late transition metal on the right, they become metallic. And for the oxygen p band, essentially they stay relatively constant. Right? So then you can actually study, right, essentially align these energetics with the dashed line, essentially the oxygen redox, and develop essentially the barriers for electron transfer, hydroxylation, and charge transfer energy, which is critical to essentially to create to understand the energetics or energy penalty to create oxygen vacancies on the surface, right? So armed with this information, right, we can essentially develop the following understanding, right? So if you make the metal oxide more covalent, right, pushing the metal D states into the P, and you can essentially increase the catalytic activity by 2 orders of magnitude, right, in, let's say, basic solution, right? And essentially what we are doing is in a more ionic metal oxides, we only have the metal as active sites, right, that absorbed and doing essentially the deprotonation reactions. But as we make the compound more covalent, we make the oxygen also as active sites. The oxygen and on the surface and metal are equally active towards splitting of water to evolve oxygen. And more importantly, we can correlate essentially the charge transfer energy we have here with respect to essentially the energy barriers for different processes. And we understand why there is a correlation, why we reduce the charge transfer energy, make the compound more covalent, why there's a correlation in increasing OER activity. The essence is essentially, initially, we are reducing the charge transfer barrier. Right? And up to a certain point, there's no electron charge transfer barrier. And then essentially, we're limited by deprotonation from the oxide surface during the oxygen evolution reaction. Right? Essentially, we change from electron limiting, transfer limiting process to a deprotonation limited process. So this gave us a clue. Essentially, if we want to further increase the catalytic activity, we essentially need to essentially develop the surface so that the surface can essentially dehydrogenate, deprotonate more effectively, right? So there are certain cations, right? So they may have higher or lower pKa's, right? So where we can essentially modify the surface so that it can actually promote the deprotonation process and increase the oxygen evolution catalytic activity further, right? So now we mentioned metal-oxygen covalency can play an important role. It appears to be a dominant parameter in the our studies, right? So if you look at in the literature, right, so over the past 50 years, you find maybe 30 different parameters or descriptors has been proposed for oxygen evolution activity, right? So then we carry out this very simple machine learning studies out of 100 measurements, and what we find essentially out of all these studies, right? Only two parameters plays a very important role, metal-oxygen covalency and also having EG filling of the transition metal near 1. And both parameters correlate strongest with the oxygen evolution activities. So this is, I'm giving just one example, right? But we are using this type of thinking, right, essentially correlating the electronic structure of metal oxides, right, aligned with essentially redox potential with species we want to catalyze, right? So that can be species redox couples in the electrochemical environment, or it can be redox couples in a chemical environment, right? For example, we can align the redox of, let's say, CO oxidation, right, or NOx redox, and utilizing essentially these energetic arguments to design a new catalyst. And more importantly, we find all these reactions, oxygen reduction, oxygen evolution, NOx, CO, they're not independent. Essentially having a stable surface that can easily manipulate or create or filling oxygen vacancies on the surface under reacting conditions is the key to essentially enable high turnover frequencies, right? So these type of thinking also allow us to take the learning from one reaction and help design other catalytic activities. So I want to just draw a connection between what we do in catalysis, which is essentially playing with electronic structure of metal oxides and changing the energetic of metal oxides and oxygen to essentially lithium-ion batteries. So lithium-ion batteries, we have similar metal oxides, right? Except here we are looking at lithium-containing metal oxides, right? And they're next to organic electrolyte, let's say EC or EMC. Right? And we find there's interesting correlation between also the covalency of these oxides, right? So the more you charge the battery, the metal oxide become more covalent, and we find there's increasing driving force for the metal oxide surface, essentially to dehydrogenate the solvent, right? Essentially to take a hydrogen from the solvent and create a proteic species on the metal oxide surface. And the driving force you can see is up to 3 eV or 300 kilojoule per mole, right? It's very high driving force. And this is one of the reasons that if you develop these high energy nickel containing positive electrodes, you can actually have a poor cycle life because of generation, we believe, of these proteic species and react with the salt and generate essentially surface films with very high impedance that influence cycle life. You can do more, and essentially we have computed over 100 of these compounds. Essentially this correlation that we develop holds, right? It's really, you can actually simplify the reactions just looking at hydrogen binding onto different metal surfaces. And this type of thinking essentially allow us to develop stable surfaces on positive electrode materials, right? So here we want to essentially minimize the oxygen reactivity, right? So if you see the lithium-ion batteries, after cycling, typically you see a rock salt. And rock salt is a surface stable against electrolyte. As you can see from the previous chart, this actually has a minimum driving force for dehydrogenation, right? So very little energy gain for hydrogen to absorb onto the surface. And that allows us to essentially design a surface coatings for positive electrodes, combining with the previous design principle for lithium conductors. Essentially, we want to design the coating that is stable, but also conducting lithium. Right? So this is really some of the ongoing work. So I want to end this presentation by coming back to the fundamental. Right? So far we have seen a correlation of bulk electronic structure to some surface activity, right? So one would argue, what are the active sites? How would we define active sites? Or how would really the surface would change its functional potential? And this is some investigation that we have been doing using single crystal surface, combining electrochemistry, in situ investigation, and the DFT. And this is also the work of Manuel, who's working at SunCat. So we utilize these in situ cell you use these in situ cell flow cells on the synchrotron. Then you can actually look at a single crystal surface, how they change as functional potential. Right? So essentially, this is a CV, a cycle of atomogram of ruthenium-110 surface, and at a different potential, essentially you can collect crystal truncation rod spectra, which is really just in situ surface diffraction. Okay? And you can actually collect a rod that if you, let's say you collect a rod of O1L type of rod, you can see is the rod's spectra, they're actually changing as a function of potential. It means it's sensitive to the surface or surface changes. It's a rod that's very sensitive to the scattering of oxygen. Right? And similarly, if you look at 10L rod, it's also changing as function of potential. Utilizing this information, what we can do is we can deduce really the oxygen distances bound to the Cus ruthenium and to bridge ruthenium. Initially at a low potential, right? So like low potential here is essentially you have a surface, typically you might have some water absorbed on the surface of ruthenium dioxide. So as you can see from the measurement that you have essentially on the Cus side, you have some oxygen bound quite long distance away, and then on the bridge, a little shorter. And as you increase the potential, as we know that it gradually will oxidize water, right, to become OH and O and O2, right? So essentially you see the oxygen is actually getting shorter, right? And then at 1.5 volt, essentially the turnover potential for oxygen evolution, we see a O2-like species absorb onto the Cus side. Right? To support this fitting of experimental data, Manuel performed a DFT calculation of this particular surface, right? So essentially Porbet diagram of the surface, and then you can see essentially on the Cus side, we have water absorbed onto the surface, and we have OH absorbed onto the bridge side. So you have a long oxygen and a little shorter oxygen. As you essentially increase the potential, you gradually deprotonate the water and deprotonate OH to form water, OH, or OH and O onto the Cus and the bridge side respectively. Right? You can further deprotonate to form OH and O. And very interestingly, at the oxygen evolution potential, we do find that this O2 species, right, and stabilize essentially by the OH on the neighboring bridge side, right? So one could say that under this condition, really removing this O2 from the Cus side is really limiting for oxygen evolution. Right? And essentially it's really how to remove these protons, right? Stabilizing this O2 is really limiting. Right? And this is, to our knowledge, one of the first evidence that's supporting that is this O2, right, between more like a superoxide-like species, it can be limiting onto the ruthenium-110 surface. And there's another configuration, this O2 can be stabilized by neighboring protons to the Cus side. Right? So you can perform this type of energetics landscape for oxygen evolution, and you'll find essentially that removing this O2 and is really limiting, is energetically uphill. Right. So this is essentially combining single crystal electrochemistry, in situ diffraction, and DFT studies. We can actually provide atomic level understanding of what could be the active site, right? Essentially, is Cus site is the active site, right? So Cus site, you initially have water absorbed, and gradually you deprotonate to OH and O, and then become O2, and then evolve oxygen. Where the bridge site essentially is from OH to O, and it becomes poisoned. Essentially, it becomes inactive, right? Under oxygen evolution conditions under the surface, right? So for this surface, we only have the Cus site is active site, right? So then one would argue, what if I change to different surfaces, right? So there's something wrong with the graphics. So there should be something here for the 110. If you change to the 100 surface, where essentially no longer you have a Cus and bridge site, right? You have every site is a Cus site. And essentially, we see that the energetics of these reaction intermediates would change. And particularly for the 100 surface, you can see that it no longer having a barrier, right? So for the oxygen evolution step. And if you change further into a 101 surface, you can also change the energetics so that the last step becomes downhill, but the essentially the formation of O to OOH becomes relimiting, right? So you can also change different surfaces and change the relimiting step. And what we find is that you can actually correlate essentially the oxygen evolution activity to the Cus oxygen bond density, right? So as you increase the Cus oxygen bond density, you can change the activity up to an order of magnitude, right? So this is essentially a very interesting picture. Essentially, you have a Cus site is active, a bridge site not active, right? So the question would be, can we activate the bridge site, right, through either something in the solution side or through the surface through substitution. And that's the work we're currently doing through essentially machine learning of various substituted surfaces to activate both the bridge and also the Cus site, because we know what are the energetics for the reaction intermediate need to be. We need to know the sites or the density of the states for each site required for optimum oxygen evolution reactions. So I want to essentially end by saying that so far we've been discussing really manipulating the electronic structure of solids, electronic structure or phonon structure of the solids. And we've been doing in the past 5 years quite a bit into chemical physics of liquids, right? So this is one example that if you essentially with the same reaction, right? So this is the reaction of hydrogen evolution. If you change the cations in the solution, you can change the reaction kinetics by many orders of magnitude, right? So without really changing the reaction, but changing the water structure, you can change the reaction kinetics. And that's, we believe, has to do with changing really the entropy change, influencing the entropy change of such half-cell reactions. So this is one area that we're going into. And lastly, right, in inorganic chemistry, right, for playing with metal oxides, we can, for a given valence state, right, different structures, we can only change the transition metal, let's say manganese energy levels, let's say 3+ or 2+, by maybe 0.1 eV across the different crystal structures. Or by utilizing, for example, biology, right? If we can stabilize these small clusters, right? As you can see through these redox of these metal clusters, these are manganese, oxygen with X. So X could be strontium, calcium, zinc. Essentially, these ions, through an inductive effect, they can modify the metal-oxygen bond energetics, right? So then you can actually see the redox potential of the manganese can change by 1 eV, right? So that's essentially means that by changing different cations, inductive cations, we can change energetics by 1 eV. That gave us huge tunability to essentially make manganese, typically inorganic metal oxides are not very active for oxygen evolution, and make it active for oxygen evolution, such as in photosystem 2. So I want to end to give this a picture. We want to connect the bulk electronic structure with the different reactivity, and in particular, we want to play with the electronic structure and also the structure, the solvent structure of the liquids, and essentially influence the electrified double layer, electrified interface, and influence the kinetics of these reactions. So I think this is particular exciting time with all the developments we have in science, right, in storage technologies, and coupled with other investments, right? So let's say electromobility, autonomous vehicles, Internet of Things, machine learning, AI, right? I think it's a particularly exciting time to think about perhaps in the next 20 years or 30 years, we might have a completely different energy landscape, right? So from the current centralized energy generation distribution to potentially distributed energy generation, energy use, right? So there are studies looking at these microgrids, right? Can we envision that we will use energy differently, right? So can we use energy as how we think about, let's say, currency, right? So can we actually trade, let's say, the energy back and forth, right, between the users and also among the different technology, right? So right now we are taking the electricity from the wall. We don't know what type of electricity, how it's generated. We can no longer putting whatever the energy we generate back into the wall, right? So it's in the future, with these development, one may envision a technology, let's say maybe, I don't know, maybe it's a bad analogy, like say WeChat, right? So you can actually utilize some software that allow you to go back and forth and have, really decision making with the type of energy and how you may want to utilize your energy, so you have more personalized energy. So this is one of the sort of outlook that my group put together from last year, right? Essentially, how we would utilize essentially renewable energy and chemical transformation to have a more sustainable living, right? We were even very ambitious with formation of fertilizers, that they will have a three-dimensional vertical farming. Right. So with that, I just want to thank you for your attention, and particularly want to thank Kelsey, Reshma, Alexei Grimo, and Seha for the phonon densive states work, Wesley for the charge transfer energy and increasing metal oxygen covalency work on oxygen evolution activity. And thank you.
Thank you very much, Professor Shao-Horn, for that fascinating deep dive into the cutting-edge research going on in the electrochemistry of energy storage technologies. We really appreciate it. And thanks for the optimistic tie-in to how this might influence the way the world evolves sustainably. Any questions? We have student questions. You look like a student, an advanced student, but a student.
So you showed that the factors have a lot of the catalyst and the line of the redox potential. But in my understanding, the electrolyte is more like a metal, so they will form some band alignment and maybe some shocking barrier. And also, at the surface, there will be some like coupling bond that will be any pinning of Fermi level, and will that effect be considered? So you just showed the band structure and didn't show any, but how the band structure aligns with the redox potential. So will that form any barrier because of some pinning of Fermi level?
Very good question. So as I shown through the theory of oxides, the left-hand side of these oxides from the early transition metal, they're semiconductors, right? So the semiconductors, so if you want to essentially, you want to oxidize something, right? You have to take something from the Fermi level redox potential of the solution, right? You have to take electron, put it here, right? So there's a barrier to do that. And there's a very nice correlation that we've seen between the energetics, this barrier, to the Tafel slope. Right, so the greater this energy barrier, the greater the Tafel slope, right? For the most active catalysts, typically they're metallic, right? So there's no barrier. So typically you can look at the Tafel slope for most metallic oxides around 60 millivolt per decade, right? So there's no barrier. So of course, you could say that for the semiconductors, we should draw the diagram of look at band bending, but this is aspect we have not done, but we focus on most of these metallic metal oxides, right? Because they have, even within these metallic oxides, the OER activity can vary by 1 or 2 order magnitudes, right? So the reason we propose is the ability to deprotonate on the surface.
Other questions?
Hi, very good, very interesting, impressive. I almost went there. Let's go back to a fundamental thing. Why are you aware of the work that's being done in, let's say, single electron storage and graphene supercapacitor, ultracapacitor, like a USPCLA, where they don't mess around with moving ions, which are huge, compared to electrons? Because that's what we really want on the surface, is electron flow. Right? So, have you done anything with storage that way?
Yeah. So right, that's great. So what about storing electrons utilizing the interface, right, just through the double layer, right? So typically, conventionally, there are 2 different type of electrochemical capacitors. One is, let's say, utilizing graphene, and where you can actually just looking at ion absorption, right? So ion absorption, if you think of ion absorption, then the amount of charge transferred is very small, right? So typically, even we use a single layer of graphene, right? If you do these type of calculations, the energy numbers will be much lower than what I showed for lithium-ion batteries, right? And in addition, I've done the calculation. Now, if we look at some of our early work, maybe 10 years ago, we have been functionalized graphene with oxygen, right? So essentially, having oxygen groups on the surface, they can essentially bind with the cations to form covalent bonding, and that can also give you more energy. Right, so this is going to the realm of pseudocapacitance, right? So you form some chemical bonds, and that give you more energy, right? So essentially, is the energy stored is essentially proportional to the number of electron transferred, right? So it's really related to how much chemical transformation, how you transform the molecule, and forming covalent bond or forming strong bonds is really important part of having high stored energy.
So one here and then I'll ask Fritz to help it up.
Is your AI model practical? Meaning, do you correct for the supply-demand problems related to some of the elements?
We have not done at that level, right? This is something we like to do. And so we are, within the M.I.T. Energy Initiative, we like to see how we can leverage the strength we have at M.I.T. and also the Energy Initiative, right? For example, these are, again, some of the visions we like to go forward, right? We have not completed the work, right? So this is more of outlook going to 2050, right? So some of the ideas might be, now we are having battery manufacturers to make sort of certain batteries, right? Technology for cars, but not all equal, right? So for example, cars, let's say in San Francisco, might drive may be driven differently, for example, in Paris, right? So how can we actually have enough data to have personalized the technology and potentially, so that's on the technology side, but also from the use side, so how would we personalize our energy use as well, right? So that's really some of the thinking out there, right? It's really, I think the first step is pattern recognition, and we're not there yet to do techno-economic analysis.
Just a quick question. You very nicely summarized various descriptors for, say, turnover frequency for ion transport. But electrochemical systems has also one disadvantage. They tend to be unstable. They decay over time. Can you think of some good descriptors to describe structural stability of the electrochemical systems?
Yeah, so that's great, right? So in fact, so when we look at, so let me just go to this slide, maybe. Let's say 30. So this is a descriptor for stability, right? So essentially, we can actually think of how to change the electronic structure of a metal oxide surface and decrease the driving force to dehydrogenate the solvent, right? So essentially, we want to have all those rock salt on top. We don't want anybody like this, right? Because here you have a large driving force of negative or 3 eV of driving force to dehydrogenate, right? Essentially take the hydrogen away from the solvent and generate a proton on the oxide surface, right? So this is essentially, in essence, a design principle for the stability of the oxide surfaces against this particular case. Now, if we want to design stable solid-state electrolyte, right? So how do we do that, right? Especially these superionic solid-state electrolytes, they have sulfur and they're not very stable, right? So what we are campaigning or testing this idea is we want to essentially lower the phonon density states of lithium, but we want the framework to be actually have the frameworks to be very hard, right? So essentially for, let's say for the case of olivine structure, for some reason for olivine structure, the structure is very hard, very high frequency, but lithium somehow in olivine is very soft. Right? So this is where is one compound where we're trying to decouple essentially the softness of lithium from the softness of the matrix. Where in the sulfides, it's very difficult to decouple because in fact the lithium band center is very soft in sulfide because it's brought by the lowering of the anion band center. Right? So essentially these two are coupled. When you have a lower anion band center, meaning anions are very mobile. Right? So meaning they're likely to have high kinetics to react.
But you will also expect some mixing of the phonon modes when you have high energy and low energy phonon modes that will certainly interact in some form.
Absolutely, absolutely. So essentially for the low superion conductors, they becomes no longer discrete. Right? But maybe for stable compound, we do want them to be discrete. We want the structural cations to have a high frequency.
With that, I think we're out of time, so I'd like to